BS Applied Mathematics 3-2, and we will present our proofs.
Consider the discounted stock price D of t S of t of 5.2.19. In this problem, we derive the formula from 5.2.20 for small d quantity of d of t S of t by two methods. First is define f of x is equal to s of 0 e raised to x and set s of t is equal to integral of 0 to t sigma of s d of w of s plus integral of 0 to t alpha of s minus r of s minus 1 half sigma squared of s d of s.
So for the proof, we first recall the properties of stochastic calculus. The first one is dt times dt is equals to 0, dt times dw is equals to 0, and the last one is dw of t times dw of t is equals to dt. Then we focus on the stochastic differential equation given, wherein it is dx of t is equals to sigma of t times dw of t plus the quantity of alpha of t minus r of t minus half of the sigma squared of t dt. Then we consider the function f of x is equals to s of 0 times e raised to x. This exponential function where s of 0 is a constant. Then we derive the function. We need to find the first and second derivative of f of x. The first derivative of f of x is equals to f of x, wherein the second derivative of f of x is equals to f of x. So f of x is equals to the first derivative and second derivative. Then we now apply the ITO's lemma, and using ITO's lemma, which is essential for the stochastic calculus for finding the differential of a function of a stochastic process, we apply it to the f of x of t is equals to s of 0 times e raised to x of t.
So by using the e to Dublin's formula to compute for dfxt, we get ddtst equals dfxt. We change the dfxt to f prime xt dxt plus 1 half f double prime xt dxt squared. We change the fxt's to so e raised to xt. Then the so ext we change it to dtst. And the dxt we change it to the one we get earlier, the sigma t dwt plus quantity alpha t minus rt minus 1 half sigma squared t dt. We get dtst quantity sigma t dwt plus quantity alpha t minus rt minus 1 half sigma squared t dt plus 1 half sigma squared t dt plus 0 plus 0. We simplify, we cancel the negative 1 half sigma squared t. We get dtst quantity sigma t dwt plus alpha t minus rt dt. The sigma t, we put it outside the quantity, and we use omega here to simplify the alpha t rt over sigma t. And the final answer that we got, d of f of xt is equals to dtst sigma t dwt plus omega t dt.
For exercise 5.1 part 2, the given problem states that, according to Ito's product rule, the differential of the product of d of t and s of t is equal to s of t times the differential of d of t plus d of t times the differential of s of t plus the product of the differentials of d of t and s of t. It also states that we have to use the given equations 5.2.15 and 5.2.18 to work out the right-hand side of the equation. Okay, to start with the proof, we have the given equations from the book of Steve Shreve. First being the differential of s of t equals to alpha of t times s of t times dt plus the sigma of t times s of t times the differential of w of t. And the second equation being the differential of d of t equals to negative r of t times d of t times dt. Now, using these given equations, we need to find the differential of the product of d of t and s of t using the product rule in Ito's calculus.
So first, we take x, which is equal to the product of s of t and the differential of d of t. Then using the equation 5.2.18, we get s of t times the product of negative r of t and d of t times dt, which results to the product of negative r of t, s of t, and d of t times dt. We then take y, which is equal to the product of d of t and the differential of s of t. Now, using the equation 5.2.15, we get d of t times the product of alpha of t and s of t times dt, plus the product of sigma of t, s of t, and the differential of w of t, which then results to the product of alpha of t, d of t, and s of t times dt, plus the product of sigma of t, d of t, s of t, and the differential of w of t.
So lastly, we consider the product z equals differential d of t multiplied by differential d of s of t using Ito's lemma, which is a rule in stochastic calculus for handling products of stochastic differentials. Given the expressions differential d of t equals negative r of t multiplied by d of t dt and differential d of s of t equals sigma of t times s of t times differential of d of w of t where differential of d of w of t represents a small change in Brownian motion process. So calculate z. So z is equal to differential d of t times differential d of s of t equals negative r of t d of t dt multiplied by the quantity of sigma of t s of t differential of d of w of t. So since dt and differential of d of w of t are orthogonal into calculus, so we have z equals 0. So we use Ito's lemma to find differential of d of t multiplied by s of t. So Ito's lemma allows us to find the differential d of t times s of t by decomposing it into deterministic and stochastic components. So decompose differential d of t multiplied by s of t into parts x, y, and z. X equals negative r of t multiplied by s of t times d of t dt. Y is equal to alpha of t d of t times s of t dt plus sigma of t multiplied by dt times s of t times differential d of w of t. Z is equal to 0 as previously calculated. So we combine these components to get the final expressions equals to differential d of t multiplied by s of t equals d of t times s of t times the quantity of alpha of t times negative r of t dt plus dt multiplied by s of t sigma times sigma of t times differential of t of w of t. That's all. Thank you.
Exercise 5.3. According to the Black-Scholes-Merton formula, The value at time zero of a European call on a stock whose initial price is S of 0 equals X is given by this expression C of 0x, where D plus of Tx adjusts the expected future volatility of the stock and D minus of Tx is interpreted as the standard deviation of the stock price over time. Using the stock price model S of t, which is modeled as a geometric Brownian motion W tilde under the risk-neutral measure P tilde, given the constant volatility sigma greater than 0, the interest rate constant R, the call strike K, and the call expiration time T, the formula for the call option at time 0 can be derived into the following expression. The following proof will provide an alternative way to compute for the call option at time 0. For exercise 5.3 item 1, we begin with the observation that if the payoff function h of s is equal to the positive part function s minus k, then h prime of s is equal to 0 if s is less than k, and 1 if s is greater than k. But if x is equal to k, then h prime of s is undefined. But such will not matter in what follows because the stock price model at time t has zero probability of taking the value of k. Using the formula for h prime of s, differentiate inside the unexpected value in 5.9.2 to obtain a formula for c sub x of 0x. So now onto the proof. Given the expected value in 5.9.2, the derived call option at time 0 is given by this expression. We also define the stock price model at time t, S of t, as follows, and the given payoff function h of s as shown.
Now differentiating the expected value, the call option at time 0 would be equal to this expression. So, by Leibniz rule that if two functions f of x and g of x are differentiable n times individually, then their product is also differentiable n times. Simply, Leibniz rule generalizes the product rule of differentiation. So, from this, we can differentiate the expression inside the expectation. And we can rewrite the expression as call option at time 0 is equal to the expected value times the quantity of discounted expected payoff derived from the payoff function of stock price expiration or the h of s of t. Applying chain rule to the derivative where the derivative to be solved is the payoff function of h of s of t or the stock price expiration, we get this expression. Now, we also know that the payoff function of h of s has a derivative such that h prime of s is equal to 0 if the stock price is less than the strike price k, and 1 if the stock price is greater than the strike price k. Then, deriving the stock price expiration s of t, we will have this equation. And the derivative of h prime of s of t is equal to 1 if the stock price of t is greater than strike price k and 0 otherwise. So we can write this expression using the indicator function as 1, where the indicator function 1 came from the derivative of stock price expiration. Hence, the h prime of stock price expiration is equal to the indicator function 1 of s of t that is greater than strike price k.
After solving for the derivative, we then get the delta function c sub x 0, x is evaluated to this expression. Then, we factor out the deterministic factor e raised to negative 1/2 sigma squared times t. After that, since w tilde of t is normally distributed from with mean equals to 0 and variance equals to 1, we let z equals w tilde of t over square root of t. Now, the expectation is converted to integral over the normal distribution function with z normally distributed with mean equals 0 and variance equals to 1. We then combine the exponent outside the integral in negative z squared over 2 plus sigma times square root of t times z inside the integral. Then solving the expression inside the integral, we then get the integral of 1 over square root 2 pi times e raised to negative z squared over 2 evaluated from d plus of t comma x to infinity. We can now evaluate this normal distribution function at d plus t comma x. Finally, the delta function c sub x of 0 comma x is equal to normal distribution function at d plus of t comma x. Now that concludes the proof for the first sub-item of exercise 5.3.
For exercise 5.3, item 2, show that the formula you obtained in item 1 can be rewritten as C sub x quantity 0 to x is equals to the probability that the asset price S at time t is greater than the strike price K, where P hat is a probability measure equivalent to the risk neutral P. Show that W hat of t is equals to W of t minus sigma times t, where sigma is constant, is a Brownian motion under P hat.
To start the proof, we assume P hat is a probability measure equivalent to P tilde and let Z of t be a radon-Nicodim derivative. According to lemma 5.2.1, the expected value of an f of t measurable random variable y satisfies E hat of y of t equals E tilde of Z of t times y of t.
We note that I sub s of t less than k is f of t measurable, and thus we can write p hat of s of t less than k is equal to e hat, open and close bracket, I of s of t less than k. Simplifying this expression, we have c sub x of 0 comma x.
So we can see that z of t is given by the exponential of sigma times the Brownian motion w tilde of t minus half of sigma squared times t. This radon-Nicodim derivative actually plays a significant role in the Girsanov theorem. Specifically, Girsanov's theorem tells us that z of t acts as the process that transforms a Brownian motion under the original probability measure into a p hat Brownian motion. Now, in the second equation in this page, as we can see in the next line, the new process w hat of t is defined as the original Brownian motion w tilde of t minus sigma times t. So this change of measure effectively shifts the drift of the Brownian motion. Therefore, it's this property where z of t meets all the required criteria for this change of measure that makes it crucial for defining the change of measure in the equation 1.
We need to rewrite the stock price at time t in terms of standard Brownian motion at time t and show that the probability of S of t is greater than k equals to the probability of negative W of t over square root of t less than d plus t and x equals to the n d plus t and x. For the proof, we first assume that the S of t follows a geometric Brownian motion using the W of t equals to standard Brownian motion at time t plus delta t, which means that the S of t equals to S of 0 exponential of delta times the W of t plus delta t plus r minus 1 half delta squared times t is greater than k, where the W of t is standard Brownian motion. Substituting the value of S of t to the equation, we have the probability of S of t greater than k equals to the probability of S of 0 exponential r minus 1 half delta squared times t plus delta times W of t is greater than k.
Okay, note that the initial set price S of 0 or simply x is equals to S of 0. We can now write the probability as probability S of t greater than k is equal to probability of S of 0 exponential r minus 1 half sigma squared t plus sigma w of t greater than k. And then dividing both sides by x is equals to S of 0 and taking the natural logarithm, we get probability of S of t greater than k is equal to probability of r minus 1 half sigma squared times t plus sigma w of t greater than ln k over x.
For the next step, we isolate the standard Brownian motion of t, which is denoted by the w hat of t. Now, the probability S of t greater than k will now be equal to the probability of w hat of t greater than ln of k over x minus the quantity r minus 1 half sigma squared times t all over sigma. Now, to get closer to the desired outcome, we will divide both sides of this equation by square root of t, which can be seen below.
For the last part of proof number 3, since d plus of t and x is equals to ln of x over k plus the mu minus 1 half of sigma squared times t over all over sigma times the square root of t, and since the negative of w hat of t over square root of t follows a standard normal distribution n of 0 and 1, we get probability of w hat of t all over square root of t greater than d plus of t and x, which is equals to n of d plus t and x. Then the inequality will change its direction since we will change the sign of wt over square root of t. By doing that, we have shown that the probability of s of t greater than k is equals to the negative of w hat of t all over square root of t is less than d plus of t and x is equals to the end of d plus of t and x. And that concludes the proof of exercise 5.3.
For exercise number 5.4 that deals with Black-Scholes Merton formula for time-varying non-random interest rate and volatility, consider a stock whose price differential is the derivative of stock S of t is equal to the interest rate R of t times S of t dt plus the volatility sigma of t times the derivative of W tilde of t, where R of t and sigma t are non-random functions of t and W tilde, and W tilde is a Brownian motion under the risk-neutral measure P. Let t greater than 0 be given and consider a European call whose value at time 0 is C of C 0, S of 0 is equal to the expected value of E raised to the negative integral of RT dt from 0 to t multiplied by S of t minus k. For sub-item number 1, show that S of t is of the form S of 0 times e raised to x, where x is a normal random variable, and determine the mean and variance of x. So to prove this, let us consider the derivative of the natural logarithm of S of t, and using Ito's lemma, which is equal to the derivative of Ito's process, that is f of t, x of t, is equal to the time derivative of t, x of t plus the first derivative of t, x of t dxt plus 1 half of the second derivative of t, x of t dx squared t.
Applying the Ito's lemma, we have the derivative of natural logarithm of s of t is equals to 1 over s of t with respect to s of t plus derivative of 1 half quantity negative 1 over s squared of t with respect to s of t. Applying stochastic differential equation with s of t, we will get r of t dt plus sigma of t derivative of w tilde of t minus sigma squared over 2 derivative of w tilde of t derivative of w tilde of t. Simplifying the terms, we will get quantity r of t minus sigma squared of t over 2 dt plus sigma of t dw tilde of t.
Continuing from the previous slide, we take the integral of both sides of the equation. Hence, we get that the natural log of s of t is equal to the natural log of s of 0 plus the integral of the risk-free interest rate r of t minus sigma squared of t divided by 2 from 0 to t plus the integral of the volatility function sigma of t multiplied by the derivative of w tilde of t from 0 to t. Then by the exponential and logarithmic property, we get the value of the stock at time t in the form of s of 0 times e raised to x, where x is the integral of the risk-free interest rate r of t minus sigma squared of t divided by 2 from 0 to t plus the integral of the volatility function sigma of t multiplied by the derivative of w tilde of t from 0 to t.
Moreover, by the theorem 4.4.9, which is Ito's integral of deterministic integrand, the integral from 0 to capital T of sigma of t with respect to the derivative of w tilde of t is a normal random variable with means equal to 0 and a variance of the integral from 0 to capital T of sigma squared of t dt. This implies that x is a random variable, normally distributed with mean equal to the integral from 0 to capital T of r of t minus sigma squared of t divided by 2 dt, and variance equal to the integral from 0 to capital T of sigma squared of t dt. And that concludes the proof for exercise 5.4, sub-item number 1.
Now, let's proceed to the second part of the exercise 5.4. We are given, let the Black-Scholes-Merton with parameter t, xk, r, and sigma to be equal to x times n, quantity of 1 over sigma squared t multiplied by the logarithm of x over k plus the quantity of r plus sigma squared over 2 multiplied by t minus e raised to negative big R t k times n quantity of 1 over sigma times square t multiplied by the logarithm of x over k plus r minus sigma squared times t. Denote that the value at time 0 of a European call expiring at time t when the underlying stock has constant volatility sigma and the interest rate r is constant show that C with parameters 0 and S0 is equal to the Black-Scholes-Merton with parameters S0, T, 1 over T, times the integral from 0 to T of RT, and the square root of 1 over T multiplied by the integral of sigma squared T from 0 to T. So we start with the proof. To simplify notations, we denote R, or the big R, to be equal 1 over T times the integral of RT from 0 to T, and sigma to be equal to the square root of 1 over T multiplied by the integral of sigma squared T from 0 to big T. Then x is normal with mean big R times T minus T sigma squared over 2 and variance of T times sigma squared. Now, we can denote C0, S0 to be equal to E hat multiplied by E negative small r times T multiplied by the positive part of ST minus K. And if we expand this, we can denote this by E raised to negative small r, negative small negative r times T over the integral over the region x such that ST is greater than or equal to K 1 over square root of 2 pi sigma times square root of T S0 times E raised to negative E times X minus K multiplied by the exponent or the exponential function of negative x minus rt plus t sigma squared over 2 square all over 2t sigma square.
Continuing from the last slide, which is equal to s of 0 multiplied by the integral over the region s of t is greater than or equal to k, e raised to negative rt over the square root of 2 pi times sigma times the square root of t multiplied by e raised to x and multiply it to the exponential equation of negative x minus capital RT plus t times sigma squared over 2, which that equation is raised by 2 over 2t times sigma squared dx minus key e raised to negative RT multiplied by the integral over the region s of t is greater than or equal to k, 1 over square root of 2 pi times sigma times square root of t multiplied by e raised to x and multiply it to the exponential equation of negative x minus capital RT plus t times sigma squared over 2, which that equation is raised by 2 over 2 times sigma squared dx. Now, the integral expression above is just equal to p of x greater than or equal to ln of s of 0 over k and equal to p of s of t greater than or equal to k.
Next is it is equal to the probability of dividing the difference between x and the quantity rt minus half of t times the square of summation divided by the summation of the square root of t being greater than or equal to the ln of k divided by s of 0 minus rt minus half of t times the square of summation divided by the summation of the square root of t. Next is it is equal to the probability of the difference between x minus rt minus half of t times square of summation divided by the summation of the square root of t being less than or equal to the ln of 0 divided by k plus rt minus half of t times the square of summation divided by the summation of the square of t. It is also equal to the natural numbers of 1 divided by the summation of the square root of t times ln of s of 0 divided by k plus rt minus half of t times the square of summation. And integral of x with respect to s of t being greater than or equal to k of e raised to negative rt divided by the square root of t pi times the summation of square root of t times e raised to x times exponential of dividing negative x minus rt plus t times the square of summation divided by 2 raised to 2 by all over 2 of t times the square of summation multiply both sides by dx. Integral of x with respect to s of t being greater than or equal to k of 1 divided by the square root of 2 pi exponential of dividing negative of x minus rt minus 2 times the square of summation divided by 2 raised to 2 all over 2 of t times the square of summation multiplying both sides by dx
is equal to 1 over square root of 2 pi times the integral from ln of s sub 0 over k to infinity minus the square of x minus r times t plus t summation squared over 2 all over 2 times t summation squared dx is equal to p times x minus the sum of r times t and 1 half t summation squared all over summation of square root of t greater than or equal to ln of k over s sub 0 minus the sum of r times t and 1 half t summation squared all over summation of square root of t is equal to T times X minus the sum of R times T, and 1 over 2 T summation squared all over to summation of square root of T is less than or equal to ln of S sub 0 over K plus R times T, and 1 over 2 T summation squared all over summation of square root of T is equal to N times 1 over summation of the square root of T times ln of S sub 0 over K plus the sum of R times T and 1 half T summation squared. Therefore, by substituting the equation 2 and equation 3 into equation 1, we have the European call is equal to BSM, or the Black-Scholes model, T S sub 0, K, and the constant rate and the volatility.